This week's episode is about how simulation is accelerating eVTOL powertrain development. And with me is my colleague Gernot Maier from AVL's headquarters in Austria. Gernot, welcome.
Thanks for having me. Hello, everyone.
And maybe a super brief introduction from your end so people get to know you.
Yeah, so thanks for the introduction. My name is Gernot Maier, and I'm, as you said, sitting in Graz here. I'm a senior technical sales specialist for battery. That means I'm more or less bridging this gap between our customers and our development team, executing customer projects, and also listening to our customers and, let's say, forwarding the requirements towards our development team, such that we always stay, let's say, on cutting edge with our features in the software.
Yeah, excellent. Yeah, super happy to have you today. And also our topic today, which, as I already mentioned, is about eVTOLs and how simulation can accelerate the powertrain development. And I want to start with a slide summarizing the challenges that the industry here faces. So this is from a presentation that was done by Horizon Aircraft at the recent Electrified Aircraft Symposium in Oshkosh. It's really an interesting list of topics and that they identified here as challenges, and also I highlighted here in black a little bit the topics where especially here simulation can help to solve the challenges and problems. So we have topics as EV or hybrid electrification, the flight controls, the battery energy density and thermal runaway, the entire whole aircraft thermal, noise, reliability, and specifically about the battery, we'll talk a lot today. And Gernot has some very interesting work that he can share here coming up. But yeah, going into a bit into the different topics. In terms of e-motor, AVL has a long competence of capabilities and services that we offer for the ground mobility, but also especially the aviation industry. And here simulation topics with regards to the e-motor in terms of thermal, mechanical, the electromagnetics, or also noise, vibration, harshness are really a long running topics that we use. And just to bring one example how we use simulation, that space is AVL's e-motor tool, where we use a combination of 3 different simulation technologies, CFD, system simulation, and also multi-body dynamics in a combined workflow to very quickly get from some design sketches of an e-motor to a really detailed thermal analysis, and then also potentially acoustics analysis, as well as a fast-running 1D system simulation model. Another very important topic, as it was mentioned by Horizon Aircraft, was the power electronics parts. So especially the thermal parts, the electrical circuits, and the EMC topics are areas where simulations can help developing. And especially also here, I brought some examples how we can help the developers. Here you see spreading of a grease or a thermal interface material for a chip, for example. So this was done in AVL's Brian lab. And this also allows them to do studies based on the performance of the thermal interface material. So if you have great contact, or maybe just there's a poor performance insulation material, what would be the difference in terms of temperature distribution? And this we do in traditional CFD here as an example in AVL FireM. And this lays the groundwork really for long-term reliability also of these chips and power electronic components. And especially mentioning here maybe a 3D to 1D modeling workflow. So you see the very detailed CFD simulation here in AVL Fire on the left side. But then also we have a workflows or multiple workflows in place to speed this up, to make reduced complexity models, let's say it like this, in system simulation, with the main goal here to really get faster, maybe not as detailed, but to make quicker decisions. You see the amount of cases you can run with a 1D study compared to, for example, a 3D study. So both worlds are very important, and also how they talk to each other. But then maybe coming to, at least for me personally, the most important part of electrified aircraft or aviation, the battery. And here over the years, we had a very good experience in AVL, not only simulating and providing simulation technology, but also actually putting it to use in our engineering. So we designed and built the energy storage system of the Aviation Alice a couple of years ago. This was a battery cassette technology that we put in there. So we did some based on simulation work, the design, and then but also then put it into the aircraft and tested it. And the plane had its official FAA experimental flight approved and successfully done in 2022. So quite a while ago, I would say. The project, I think, commercially had some challenges, but the technology that we developed here, especially also on the simulation side, is since then lived on and got used by us in further projects, as well as industry partners and customers. And this brings me to the next point, actually, where I'm very delighted to share that Vertical Aerospace had used our technology for quite a while now. Gernot might share more in in the future, but yeah, especially also you might be able to talk a bit more about Vertical. So we see here a bit the information that's publicly available. So we are more than happy to share. But what they do, I think, they're based in the UK and developing really this amazing eVTOLs here, passenger eVTOLs. And I think I just play a quick video to give a bit better impression of what they do. So hopefully that works. Yeah, really amazing work that they do here. Amazing aircraft, and also amazing work that is done here behind the scenes. And you can get actually directly from Vertical Aerospace more insight in their development process. So we were very fortunate that Maria from Vertical Aerospace was sharing some of their simulation methodology, really, especially how multi-faceted it is in terms of solving their challenges in an AVL webinar that's online on demand. So you can follow the link here or simply Google it. And I think it's well worth hearing directly from them how they use it But specifically here in that aspect, yeah, we also picked a few aspects here that we can share from our development, and then also from some of the public work we did with them, and we can address especially battery design challenges upfront. In terms of selecting the right cells, weight is a big issue, lifetime modeling for total cost of ownership. And for example, we can use AVL Cruise M here to create a model of the aircraft, to make the cell decisions, and then do virtual cell comparisons here. So here's just one example with four different cells we ran on the same profile, and there are significant performance differences. So stuff like this is very helpful for the engineers to make their design decisions quickly. But then also, and maybe not also, but even more importantly, is the safety aspect. And Gernot is an expert in thermal runaway simulation, I would say, definitely. And yeah, maybe you can explain to us a bit the challenges and applications on the safety simulations.
Yeah, Thomas, as you, let's say, rightfully pointed out before, the battery is a huge topic of let's say, simulation, basically, where I can do different things. And thermal runaway is a big thing. We will go into that on the next slide, I think. But more generally speaking, there are, of course, a lot of topics you can cover using simulation that help you in your development process, either by, let's say, shortening the development time or maybe gaining insights that you wouldn't have even on the testbed, for example. And also on different levels of integration. So either on system side, for example, when it comes to developing a cooling concept and strategy that, let's say, yeah, is really taking the entire system into focus, or you can go down, let's say, to the smallest level, setting up the single cell using an electrochemical model to, yeah, observe things that you don't see on a testbed, like anode potentials that pretty much also drive how the SEI layer grows, things like that. But then also developing strategies for fast charging such that your anode potentials are always right, such that your cell doesn't age faster than it needs to be. And therefore also, let's say, estimating the temperatures and power losses in your system. Another topic of interest for sure is also getting, let's say, some insights in your model, in your battery module. What would be the mechanical stresses that arise from breathing and swelling of the battery cell? Yeah, and also not forgetting other parts in our, let's say, system, because we don't only have the battery or the energy storage system, we do have power electronics in there that needs to, let's say, make sure that the, let's say, all the currents go into the right direction. And all of these things are really, let's say, open playing ground for simulation solutions. And now if we focus more on the, let's say, thermal runaway aspect. So yeah, thanks. Thermal runaway is a huge topic, of course, or safety to be, let's say, more general. And it's not only in aviation, but also automotive or wherever you're working with lithium-ion batteries, I would say, with certain cell chemistries. And there are actually a lot of different physical effects that we want to cover, to consider, ranging from cell level effects going up to pack level effects. And we just listed here the most important ones, starting from the cell level. Of course, if a malfunction happens, the cell releases a lot of heat, let's say in a very short amount of time. And you want to make sure that this heat is going out, let's say, in a controlled manner by picking the right thermal interface materials, potting compounds, such that you are not running the risk of yeah, a chain reaction, the thermal runaway, affecting other battery cells. What goes hand in hand with that is, of course, venting and ejection of particles inside the cells, flammability and combustion risk that comes from these usually flammable species that come out of that, potential for arcing due to the particles. So in this case, we're already on a module to pack level, more or less. But these are things you need to consider. And then also other effects like plastic parts melting up and maybe providing new flow paths for the gas vent jets that you don't want to have. And then last but not least, consideration of burst disks. Where do I need to place them to make the system as safe as possible? And also which characteristic is the best one to really make sure that the pressure relief is as intended. And then also pack deformation. Because if we have, let's say, metal packs or metal housings, they might deform, and this changes, of course, the gas volume inside, and also affects the how the system behaves then in the end. All of these things can be covered using simulation, but what we're definitely not saying is that simulation alone is doing the trick. For us, it's always a synthesis between simulation and testing, because you need, of course, input data. You need some data to validate your simulation models, but still, once you have a certain maturity of your simulation model that you can rely on, you can go further and again, especially here in thermal runaway as well, investigate things that you cannot really see on the test bed, because whoever, let's say, has anything to do with thermal runaway knows it can happen that you place a thermocouple somewhere, but due to the violence of these reactions, it's thrown away and you cannot really use this sensor at this point anymore for engineering. And in simulation, this cannot happen, of course. Yeah,
there's also practical limitations to the amount, the number, simply the sheer amount of tests you can do. You might not have even that many cell samples at that point, or other physical restrictions really that but you can test a few potentially and then use it as input data and run the simulations.
That's a very good point, because as you said, putting a prototype battery pack on the test bed is quite expensive, and you don't have 100 of them just lying around. And therefore, again, this point in the middle comes into play. You can do, let's say, a single cell test to get the characteristic of your battery cell, and then put that into a bigger unit and perform tests first virtually, and then you're even more informed. And this is something we will see later on, and was confirmed also by Vertical. The simulation really also helps you to get a better understanding of how the tests should look like. That's very good point from your side.
Yeah, excellent. And I think to achieve this this amount of different effects, or we can put them to use in different simulation domains, I would say, or in really different simulation technologies. At the foundation of everything we do in terms of thermal runaway and safety simulations, we use 3D CFD, FireM in this case. These are demanding simulations, no questions. So they run on a high performance computer cluster or sort cloud, even nowadays, sort of things, or days, hours, if not weeks for a large pack, according to the amount of detail, and provide you the highest accuracy. So we are using this to really validate the design, and we want to get as close as possible to a real test with these simulations. But also we understand the engineering need of speed, and we need to find ways of getting to decisions faster. And we therefore refer to system simulations, so 0D, 1D based approaches. This can go up to a coarse 3D level, as you might see here on the image. And this runs much faster, runs maybe on a workstation or a powerful laptop in almost real time. Real time typically is the goal for this kind of simulations. Very useful for the concept phase. But even this, we like to get faster, and we use these kind of simulations for training, generating training data for neural network models, reduced order models. I use the umbrella term AI here a bit, and create tools that the engineers use to screen the entire parameter space really in an effective manner within seconds. Really, yeah, help
That's
your engineers then
a
do
good
the
entry
designing.
point.
Yeah, I think so. From an engineering perspective, you work your way basically backwards. So in tool development, it's almost left to right. In the engineering application, pretty much right. And in the end, maybe as I mentioned, CFD is the foundation. Again, can you explain us a bit, walk us through a bit how our domains are there?
If we're, let's say, in this 3D CFD realm, as you mentioned before, we're looking really into all of the details. In Cruise M, for example, we saw it in the last slide, you can do this kind of initial simulations, for example, for thermal runaway, but also for, let's say, your classical battery cooling application. You get results fast. You can cover the complexity of your geometry to a certain extent. But when it comes to assessing the performance of your already designed battery module pack, power electronics component or whatever, 3D CFD is always the way to get the most detailed insights. So if you have a look, for example, on the lower right-hand side, the busbar heating, if you have the design, the CAD model available for that, you can set up your simulation and run it in Fire in this case, and really get a spatial and also temporarily resolved temperature field, for example, but also get local current densities as we see on this exact picture, where you see, okay, orange or yellowish areas are where we have higher local current density distributions. That means also we are heating up more because more current running through is more heat generated there. And this is where it already starts. You can assess, okay, is my busbar maybe getting too hot in certain areas? Would it make sense to increase the cross section here or there, or maybe round a sharp edge or something like that? But it doesn't stop there. You can also do an analysis of how the cooling performs. So the middle picture on the lower, let's say, row shows, in this case, a simple battery module with cylindrical cells, air-cooled. So maybe not the cooling concept for a most high-performing battery modules, but still it can be done. You can assess if there is enough airflow in between the battery cells, or if you need to design some guiding channels because there is too much air bypassing and stuff like that. Yeah. On the lower left-hand side, the hazard scenarios we already covered before, but what I also want to mention is this kind of, we call it normal operation. So nothing, let's say, going wrong in terms of thermal runaway, but just a thermal or electrothermal simulation of the system. The cells generate heat, and we simulate that in conjunction with the busbar heating that I mentioned before. We simulate it also in conjunction with the cooling system. In this, let's say, animation that you see above, we have a cooling plate with liquid cooling going through. And in the simulation, and based on the input data you have available, you can pick different options how you represent the battery cell in this case. It can be a rather simple and crude model, like just saying my cells have a certain equivalent resistance depending on temperature, for example. It can be something more sophisticated, like an equivalent circuit model. These are anyway quite common, I would say, on the market because they're usually also running in battery management systems. But then it's also possible to have really kind of your virtual twins of the battery cells by modeling them as BATIMO cells, or let's say an electrochemical model that is based on a P2D model, where you really have the parameters open, where you can tinker around with that. Of course, this is more for let's say, customers who really have access to these parameters, but you can really, you cover the entire spectrum, I would say, with that.
Excellent. Yeah, thanks for the great overview. And maybe just to also give you an overview how now a system level, a faster running one would compare here. So you see on the right side, we are nowhere using a real CAD, so it's a bit more abstract. It's much more components, but it's a lot more simplified, but nevertheless it can be very useful. And yeah, just to give you an idea of how, let's say, a CFD model would translate into a rougher system simulation model. And yeah, we would use this then to, as I mentioned earlier, to train our machine learning models. And then yeah, here you see also a bit of a very complex pack model here that we used, and yet within seconds then to screen the entire parameter space. But yeah, I'm speeding here a bit as we are a bit short on time, because I rather want to show you or get to a real life application of where this was already used. And Gernot, you were involved in this project and might be able to share a bit more.
Yeah, sure. Just a comment to the last slide. I also just want to emphasize that it's really a back and forth between the different simulation tools that we have. So this is, I would really say, characteristic of how simulation is done nowadays. Sometimes it's necessary to have this detailed 3D CFD, gives you a lot of insight, is maybe taking a lot of time, therefore system simulation is faster. And we are always trying to use all the bits and pieces from one model and transfer it to another one. But anyway, yeah, we are happy to be able to give some insight into two use cases, let's say from our already quite long-standing collaboration with Vertical Aerospace. And this is now also going into this safety direction, because the question was, when you want to assess, let's say, the safety of your system through simulation, how detailed does the model need to be? For such a test module with a couple of cylindrical cells, where we trigger a few of them, is it sufficient to just say we are looking into the, let's say, solid heat conduction through all of the battery cells and housing parts? Or do we need to consider venting as well? Because the venting also is kind, of course, of an additional heat source. And wherever a gas jet hits our battery cells, they heat up. And in this specific case, you can clearly see that this ever so small, let's say, amount of additional heating through venting that you can see here in this spike, it's just lasting for a few seconds, but it can be enough that your temperature is elevated by a few degrees. If we switch to the lower graph, you can see this green solid line indicating the venting case compared to the no venting case. Just shifted it so slightly, but it still means that in this case, we reach the temperature where venting in the next cell, or thermal runaway, sorry, thermal runaway is initialized in the next cell, causing the temperature to go up rapidly. And therefore, we, again, following up on the last slide, we want to use simpler simulation models, but at some point you always need to verify or do it with, let's say, more physics behind, because there are some edge cases where this could really make a difference. The second case, if you switch to the next slide, is of course always, can I trust my simulation model? Because there are always assumptions and simplifications in. And this also always requires calibration. So if you don't know all the input, which you usually don't, like thermal contact resistance, information about how parts are touching each other, you will always need some kind of calibration. And this is just an indication of that, again, from the same module where we are tracking the signals of two thermocouples that were placed on adjacent cells. And the upper graph shows the mismatch in timing that we have before calibrating the model. So that means assuming perfect heat conduction in our simulation model, which is not representing the reality, but we also don't have this input usually. And here you can really see that we have almost 10 minutes of mismatch. So once we calibrate the model, we see on the lower chart that we are hitting this, let's say, trigger much better. And this is also something one always needs to, we always need to mention, because sometimes you might assume, okay, I'm running a simulation and whatever comes out of that is just representing reality. No, you always need to be critical about that. And that's why, again, we have this topic of simulation in synthesis with testing, because you need at some point to make sure, okay, my simulation model represents reality fairly well, and now I can continue with further tasks. And yeah, this was basically, sorry, I just wanted to say this was basically also, let's say, confirmed by Maria Odio from Vertical Aerospace, sorry, who were really, let's say, happy with that, because the simulation gave them a better understanding of the systems, the tests, different mechanisms, and so on. And it allowed them to make better decisions regarding, let's say, the further engineering tasks they are facing.
Yeah, perfect. Yeah, I was about to say something, but I think I cannot finish with a better statement than that Maria gave us here. And thanks for sharing some insight in the work that was done here. Also, thanks to Vertical Aerospace for allowing us to show some of this public here. It's not so frequent that companies are really that transparent about their achievements, especially on the engineering side. So yeah, thanks again, and also thanks to you, Gernot, again for joining us today.
Thanks.
We're at the end of
Thanks for having me.
Session, and that leaves me just with a reminder to join us again next week. We will look into hybrid electric aviation and how it can extend the range and enable new use cases and missions. Yeah, thanks again for joining, and hope to see you next week again.
Thank you. Bye.